we finish up section 4.2 by doing some examples of using Riemann sums to help us estimate the area underneath a curve. We defined Riemann sums in the last video. If you haven't watched it yet, make sure you go back and do that. In this first example today, we're going to try to use left and right Riemann sums to estimate the area between the curve f of x equals 2x squared minus 8x plus 1 over the interval from 3 to 15, where n is equal to 3. And remember, n is just telling you how many rectangles you're using to estimate this area. Now, I could maybe try to start by sketching this curve, but I don't have any idea what this looks like. And maybe you do, I don't know, you could probably put it on a computer or something, but you don't really need to know what the curve looks like to compute these Riemann sums. So let's just first consider the fact that n is equal to 3. This tells us that delta x, remember delta x is going to be the base of each of your rectangles, it's going to be the length of the subintervals. Well, delta x is always defined to be b minus a over n, where b and a are the endpoints of your interval and n is the number of rectangles. So for us, this is going to be 15 minus 3 divided by 3. Right, so 12 over 3, which is 4. So essentially, we're going to break up this interval of x values, this interval from 3 to 15, into subintervals of length 4. So I'm going to go from 3 to, if my first is a length of 4, I'm going to have to go from 3 to 7. That way the base is in fact length 4. Then add 4 again, I'll go from 7 to 11, and then add 4 again, and that gets us to 15. So we see that this does break up our interval into 1, 2, 3 many parts, which is correct, right? It should be n equals 3. Okay, now it's helpful to do a little bit of scratch work here by just sort of finding the output of the function at each of the endpoints. Right, so I'm going to just plug each one of these endpoints into the function to figure out what the output is, because those outputs are going to tell us the height of the rectangle at each of those endpoints. Okay, so I need to plug in 3 into this original function. Alright, so we'll end up with 2 times 3 squared minus 8 times 3 plus 1. Alright, you can trust me here that this is going to give you a negative 5. And similarly, I plug in 7 into this function. I get an output of 43. If I plug in 11, I get an output of 155. And if I plug in 15, I get an output of 331. Unless you think I'm really good at doing math in my head, I am not. I'm looking at the answers on a piece of paper. Alright, so you'd have to actually plug these in and do the computations yourself. Wait, but these are telling you the height of these rectangles, and this should maybe jump out at you as a red flag. What the heck does this mean that f of 3 is negative 5? The height of your rectangle is negative 5? How can a rectangle have negative 5 height? Well, just keep in mind that this is going to give you the signed area. I didn't say it, I probably should have. Signed area between the curve and the x-axis, where anything that's underneath the x-axis is negative area. So this is, if you're using this endpoint of 3, it's going to give you a negative area. That's just something to be aware of. Don't worry about it, right? It's just something to be aware of. Alright, let's start with the right-handed Riemann sum. Right, so we had said last time that the right-handed Riemann sum r sub n, where n is your number of rectangles, for us that's 3, is just going to be the result of multiplying each of the base, or the length of the base, which is always going to be 4, times the output of the function at each of the right endpoints of the interval. So for my first interval, the right endpoint would be 7, so it would be f of 7, plus the right endpoint of my second interval is 11, f of 11, and the right endpoint of this last interval would be 15, so we add f of 15. And this is just a pretty straightforward computation. Again, the 4 on the outside, that's going to be your delta x. That's the base of each of these rectangles. And using my scratch work here, it's as simple as just plugging it in, 43 plus 155 plus 331, adding them all together and multiplying by 4, I get an estimated area of 2,116. Okay, now let's do my left-handed Riemann sum. It's almost the exact same computation, only now we're using the left endpoints. Okay, so whoops, left-handed would be L sub 3, and again we're putting a 3 here because we're using 3 boxes. We'd get a different estimate if we used more boxes, if we had increased this to 4 or 5 or something else. Alright, so L sub 3 is going to be equal to that same delta x on the outside, the same length of the base of the rectangles, which is 4. But this time I'm going to use the left-hand endpoint of each interval. So the left endpoint here would be 3. So I'll have the height would be f of 3. Left endpoint of my second interval is 7, so f of 7. And the left endpoint of this last interval would be f of 11. Okay, so computing this, we get 4 times negative 5 plus 43 plus 155. Add them all up and multiply by 4, and I get an estimated area of 772. Wowzers. These are two very different estimates for the same area. Right, this is giving you one estimate of the area, 2,116. This is giving you another area, and your right-handed Riemann sum is giving you an area that's almost 3 times bigger than your left-handed Riemann sum. That should tell you something about these estimates. They're terrible. They're not good at all. If you can get such different estimates like this, it's not a very good estimate at all. And the reason for that in this case is that we're breaking up our intervals into huge chunks here. Right, so we're using 3 boxes, which means we're getting a really either huge overestimate or huge underestimate, but in any case, it's not a good estimate. We really want to use smaller and smaller intervals here, right? In other words, use more and more rectangles to get a better estimate. We talked about that in the last video. And so that's why we got such a sort of varied estimates here that don't look very good. All right, now we'll do another example, and again, we're using a relatively small number of rectangles, so this next example probably also isn't going to give you great estimates, but we can still sort of use it as an example of how to do these computations. So this time we're going to find the area between the x-axis and the curve f of x equals x squared times ln of 2x, using 4 rectangles this time over the interval from 1 to 9. And again, we really want signed area, so any area below the x-axis would be considered a negative area. All right, we start off by finding our delta x, right? Remember that's going to be the base of each rectangle, and we get that by doing b minus a over n. So the right endpoint minus the left endpoint divided by the number of rectangles we're going to use. We're using 4. So 8 over 4 gives us a delta x of 2. This is a little bit better than last time. So I can take my interval from 1 to 9, and I'm going to break it up into subintervals of length 2. Right, so from 1, if I add 2, I'd get up to 3. Add 2 again, and I'll get up to 5. Add 2 again, and I'll get up to 7. I did a terrible job of drawing this. If I add 2 again, I'll get up to 9, and forget about the rest of this. I just broke it up really poorly. Sorry about that. All right, but you can see that this would really give us 1, 2, 3, 4 subintervals, all of which has a length of 2. If you drew it correctly, it would look a little more even, a little more uniform. Right, but once again, as scratch work, it's going to be useful for us if we plug in each of the endpoints into the original function and see what the outputs are. Right, so f of 1, for instance, that's our leftmost endpoint, would be 1 squared times ln of 2. Whatever that is. F of 3 would be 3 squared times ln of 6, so 9 ln of 6. F of 5 would be 5 squared ln of 10, so 25 times ln of 10. F of 7 would be 7 squared ln of 14, so 49 ln of 14. And f of 9, our rightmost endpoint, would be 9 squared, or 81, times ln of 2 times 9, 18. Okay, and you get some numbers out of here. I'm not sure what they are, but something, right? These are numbers, these are outputs. And once again, we can use these to find the right-handed Riemann sum and the left-handed Riemann sum. For the right-handed Riemann sum, R sub n, n is the number of rectangles, R is 4, so it would be R sub 4. And we use this formula delta x times f of x1, x2, all the way up to xn, which in this case would be 4. So this would be delta x is the length of your intervals. We had said that the length of each interval was 2. And then we take the right endpoint of each of these intervals here, right? So the right endpoint of the first interval is 3, so it'll be 2 times f of 3 plus the right-handed endpoint of the second interval is 5. The third interval, the right-handed endpoint is 7, so f of 7, and then f of 9. Okay, so it's 2 times all of these numbers that we had already found up here in our scratch work. 9 ln of 6 plus 25 ln of 10 plus 49 ln of 14 plus 81 ln of 18. Add those all up together, multiply it by 2, and you get something, you'll have to trust me on this, but you can double check on your own, something roughly like 407.39. Okay. And for the left-handed Riemann sums, we're doing almost the same thing, but we're using the left endpoint of our interval. So L sub 4 would give us, again, we'll have that same delta x on the outside, which is 2, but this time we'll do f of 1 plus f of 3 plus f of 5 plus f of 7. Right, we're using the left endpoint of each of these intervals, so 1, 3, 5, and 7. So this would be 2 times 1 ln of 2 plus 9 ln of 6 plus 25 ln of 10 plus 49 ln of 14. And you can trust me, whoops, that this is approximately equal to 874.25. Again, not a particularly good estimate, considering what we got down here is more than twice as big as what we got up here. Okay, but at least it's not 3 times bigger like the one we did in the last example, and we can maybe say that that's because we used more intervals, or right, we used more rectangles, and the more rectangles you use, the better the estimate you're going to get. Okay, and using that same reasoning here, the larger the n, the more rectangles you use, the better the estimate. And so we can use what we learned about limits to help us figure out the exact area by just saying, well, let's cut that interval up into more and more and more pieces, more and more and more rectangles. We're just going to keep doing it until they're basically a width of 0, right? We're going to have essentially infinitely many rectangles. And so that's the idea of a definite integral. It's essentially the limit of the right-handed Riemann sum as n goes to infinity, as you use infinitely many rectangles instead of just 3 or 4 rectangles like we've done in our examples. And it turns out that the limit of the right-handed Riemann sums versus the left-handed Riemann sums ends up being equal to each other. We're not going to prove that, but maybe someday in analysis. And so we call that limit, whatever that is, we call that exact signed area under the curve the definite integral of f from a to b. And so the notation that we use here is going to look familiar to you because this is without the a and the b here, without the bounds on the top and the bottom part of this stretched out s symbol. This looks like the notation that we used when we were talking about antiderivatives, right? But if you actually put a number here and a number up here, now this becomes the definite integral from a to b, and it represents the area between the curve f of x and the x-axis on the interval from a to b. Okay, so let's do an example. If we wanted to find the integral from 1 to 5 of 2x plus 6 dx, I just want to talk you through what this means here. this is your function, right? This is the curve that they're talking about. And so if we were to try and sketch that, 2x plus 6 is, is this supposed to be 2x minus 6 perhaps? Oh no, this is correct. All right, 2x plus 6 is a line that has a y-intercept of 6 and a slope of 2. And so it looks something roughly like this. And so if we're looking at the interval from 1 to 5, I'm going to have to scale this a little to actually get a sense of what this looks like. Well, f of 1 would be 2 times 1 plus 6, which is 8. So we've got a point on the curve here at 1, 8. F of 5 would be 2 times 5 plus 6, which is 16. So we've got a point here at 5, 16. And so what this represents here is the area between this curve, in other words, between this line and the x-axis on that interval from 1 to 5. All right, so if we sort of drop down a line here to the x-axis and drop down a line here to this x-axis, we're looking for this area here. Okay, now technically we define this based on limits of Riemann sums, but again, if this area is something that you already have a formula to find the area of that shape, then there's no need to deal with those limits or anything. Instead, what you can do is just break this up into shapes that you know the area of. Either use the area of a trapezoid formula, or maybe just say, well, this is a rectangle. The area of the rectangle is base times height. So the base is 4 times the height is 8, it looks like, right? 32. And then we also have this triangle up here. Highlight this in case it's hard to see. This triangle here, which has a formula 1/2 times the base times the height. Well, the base is still going to be 4. From 1 to 5, it's still going to be 4. And the height from 8 to 16 is also going to be 8. So this is 16. And so the total area is 32 plus 16, or 48 units. Okay? And so this definite integral that we're looking at here, this area between the curve, which happens to be a line, and the x-axis, is just given by this exact formula that we had over here. It's 48. Right? So the takeaway here is when you see this integral symbol and there's numbers on the top and the bottom, then we're looking for area under the curve. Right? That symbol with numbers at the top and the bottom represents area under the curve, as opposed to the general antiderivative that we talked about in section 4.1. And in the next chapter, we'll see exactly why they use such similar notation for both of these, why these two things are so closely linked together.